Hi everybody, today we're going to talk about topic modeling in Python. And basically what we're going to do is put together some K-means clustering, some word embeddings, and some pre-trained sentiment models from the Hugging Face platform, which interface with TensorFlow and PyTorch and stuff like that, in order to create a sort of algorithm that can read in a bunch of text data, summarize it, extract topics from that data set, and then kind of like score some sentiment and give some sort of generate some topic keywords about each topic. So what I'm showing here is the output, sort of the end result of what we're going to build up together. And so basically, we have this topic model. I've created 40 topics here, and we have keywords. So we were able to generate keywords per topic per the 40 topics. And so this one happens to be about migraines and headaches. And when we look into the actual reviews, which are down here, this is the main result, the output data frame. If we read through them, we can see, well, this one's about ringing in the ears, sensitivity to noise, and noise in the head, which all have to do with, head issues. This next one's about, they mention headache. This next person talks about how they've experienced headaches. This one's talking about, a mild headache at the start. If we scroll down further, this person's talking about how they had a severe headache. So clearly, this topic is all about headaches and like head pain and the related sort of things around that. And if we look at a different topic, topic number 8, this one says the keywords are about, eyes and cataracts and eyelids and stuff like that. So when we look here, we can see the upper eyelids, are red and itchy. So, it's talking about that. Keloid scars, I'm not sure what that is, but the next one is about burning in the eyes. Next one is about eye pain, iris atrophied, which has to do with eyes and pupils, slight change in the color of the treated eye. If you scroll down more, this person's talking about twitching of the eyes, blurred vision. So clearly, this topic is all about eyes and eye issues. You can look at just one more. That's a topic 32. Topic 32, the summary keywords have to do with sort of infections, sort of yeast infections, I guess, those kinds of infections that women can get. And so if we look at the reviews, we see this person saying they did get an infection. This person got an infection. This person's talking about how they developed one. If we scroll down more, they talk about how they had a yeast infection, chronic yeast infection. They developed vaginitis and a yeast infection. So clearly, this topic is also pretty well defined on the idea of, infections. So, I think this method works pretty well. It's pretty cool combination of different kinds of NLP tools and models that I'm going to show. So let's just hop into it, and I hope you guys enjoy the video here. Okay, so the first thing we're going to do in this tutorial is we are going to install some packages. Now, I've already done this. It takes a while for this to install if you're doing it for the first time, but these are the packages that you're going to need. The top 3 here are just TensorFlow packages. You got the Seaborn, which I may or may not use for plotting. I like to use Matplotlib, but anyway, you're going to need scikit-learn if you don't already have it for some K-means clustering. We need PyTorch, to load some sentiment analysis models through the Hugging Face platform, and we interact with the Hugging Face platform through this transformers sort of data set. I'll show you how to do that. Like I said before, Hugging Face is, I think, a relatively new platform for deep learning NLP style models. I think it has more than that, but it makes the deep learning more accessible to people that just need to use it, like practitioners and stuff like that. You can leverage pre-trained models and stuff. And now the libraries we're going to load are just your usual stuff. You got your pandas, your NumPy, your Matplotlib, and so on and so forth. I'm loading the TensorFlow packages that we need, that we installed. Now for our Hugging Face, we interact with it extremely simply through this pipeline um, handle here from the transformers. We just use pipeline. I'll show you how to do that. We're going to need KMeans, and from NLTK, we're going to need some helper stuff. So just some word tokenizers and some stop words that'll be helpful for keyword extraction later on. And for NLTK, you need to download some stuff through their like API basically. So you're going to need Punct, which helps with word tokenize, and you're going to need stop words. It needs to be downloaded, and that's all we need for this video. You can do like a NLTK download, and I think it downloads everything. which takes forever. But we're not interested in doing that in this video. That should be enough for what we're going to do here. So that's kind of what the prerequisites for this. And I've already run all this, so go ahead and take the time to do that, and then we can hop into the actual coding. So the next thing we want to do is actually we want to load up like the deep learning models. So let's do that now. So we're going to use two things. One is the Universal Sentence Encoder from Google. And so the way you can do this in Encoder, we can interact with it using the hub from TensorFlow. And basically what's kind of nice is all we need to do is pass it the query, well, URI to the model. So it's very simple. Through the hub handle from TensorFlow, we can just load the model from this endpoint, and voila, we have it. And what's interesting is they have different versions of it, and they have like a multilingual one that's useful. The way to actually use it as per their website is a function to use USC encoder, and it's just like a wrapper around it. So we'll call it embed, and we return an array like this encoder input. So essentially, what this is just doing is let's just run that and let it load it up. But if we have like some text that we want to embed, we can do like embedding equals embed, and then we can pass it the input, which I believe needs to be a list. Yeah, it needs to be a list. So let's say I love cats more than dogs, let's say. So this is our embedding. Let's print the shape of this embedding itself. So it's 512 dimensional embedding. I think there are different ones, but that's sufficient for our purposes. And here's the array. So you get out basically, the context vector, which is great. So that's how you kind of work with this. And the next thing we're going to actually print out to here. I'm going to get rid of this because we don't need it. The next thing that we're going to get out of here is the sentiment model. So get sentiment model from Hugging Face platform. And so the sentiment model is a pre-trained model. And we can, as I said before, use the pipeline handle to access it, and it's super simple. So this is from the transformers dataset that we installed before, sentiment analysis. So that's all we need to do. That's literally all. There's different parameters you can specify here, like model type and stuff like that. I'm just going to let it pick whatever default it wants to. But depending on your application, you might want to choose a model that was trained on a particular data set that's kind of like for like with what you're doing. For our case, I'm just going to take what it gives me. And note, there's other kinds of models. There's summarization models that you can load like this. Summarization, I believe. I forget the actual word here. But you can actually load different types of models very easily like that. So let's go ahead and, well, one other thing. So just like the Universal Sentence Encoder, I'm going to define a handle to kind of interact with this. We don't need to, but I'm just going to do it. So let me just get that. So you can see here that puts no model supply defaulting to this model. So this is the model it defaults to. And whatever it's being used, and let's just test it out. Sentiment model, we use the same sentence as we used before, which I think it was I love cats. Well, actually, let me just leave it as I love cats and see what it returns. So it returns label positive. So it returns, which makes perfect sense. Let's see, let's run it again, and on something that's negative. I hate cats. That returns label negative score with a confidence score. I hate cats. So it obviously works nicely. And I think I want to build a little function that lets us kind of deal with this more easily. So what I want is, let's say this is the result and it's a list. So what I want to do is return just the Sine Score. So I'm going to take the sine is going to equal 1 if result 0 label is positive, else negative 1. And the value is going to be result 0 score. And the final result, so the sentiment score is just going to be sine times value. And all I want to do here is just, sentiment, and then S for sentence, let's say. Actually, let's use input. That's fine. Input. And then we return the score. Actually, let's just go ahead and return this directly. Plus verbose. Let's just test that. Sentiment. I hate cats so much. And I forgot that. Let's go ahead. So it works perfectly fine. Let's write, I love cats so much. It works perfectly fine. Great. Let's just commit this here. So we'll use that in our work below. So next, we're going to focus on loading up the data and getting a view of what that looks like. So let's go ahead and get that started. So I have the data set here. So it's the DrugLib trained data set that I got from the UCI machine learning database. When I post the GitHub up, you'll have the link to it and all that. So, the data set will be there. But anyway, let's just load it up here. So we're going to use pandas to read it in. So it's the drug lib training data. It's tab separated, so we need to do that. And let's just take a look at the shape of this. Let's collapse that. So it's about 3,000 reviews of prescription drug reviews. That's what makes up this data set. So if we sample a bunch of them here, you can sort of take a look at what we're dealing with. So there's a bunch of columns here that we're not going to use, but they could be useful in other studies. You got things like the rating, the effectiveness that I guess is judged by the patient, whether or not there were side effects. So in this case, there could be no side effects or severe. What the condition the drugs were treating, and then there's different kinds of reviews. In our case, we want this side effect reviews, right? So this person said there's no side effects. This one had numbness and stuff like that. This person had headaches. This person had no side effects, and so on and so forth. This person had redness. So we want to basically build a model that can read the side effects and extract the different categories of side effects people are describing. And that's what we call the topics. So the topic model extraction, that's what we want to kind of work on here. And let's just limit this data to, a data set that actually we want to look at. So look at only the side effects. That's really all we want to look at. So side effects reviews. All right, so that's just going to be df side effects review. Let me make sure I got that column right. Side effects review. I love the autocomplete. Let's drop any nulls if there are any, and let's get this in a list format. And then we just kind of have that going forward as like a list that we're going to use to kind of start building our models and stuff like that. So from here, let's start. I already did that. Let's move that up. I tried to predefine the flow here. So next, let's start building the topic model. Okay, so to start this part, we're going to create a class. We're going to call it reviews topic model. And what we need to do is obviously create a constructor and so what I'm thinking is for this class, we're going to want to pass in the reviews as like input. And then what we want to do right away is create sort of a working matrix X that has like the data to work with. And we want it to be clean of the reviews. So we want to take the reviews in when we instantiate the object, and we want to take the reviews, pass them through a clean method, and get something that we can work with and reference throughout the rest of this class object. And so this is our constructor. And what we want to do is define the clean method. So the clean text method, def clean self, and then we're going to pass it in, I guess, the reviews. And so I took a look at this data before, and it's actually pretty clean. The only things we really want to remove is like small minor things like new line characters and other kinds of small things that we kind of don't care about. So I'm just going to do that real quick. So words to replace. So I'm going to define a string map. And so what this is going to have is things like this. We want to map to empty. So basically erase them. Likewise with new line characters, make them empty. Sometimes we encounter this. So like that's when you see things like, oh, I like vanilla or chocolate. What we want to map this to is vanilla chocolate. So just a space. That's all we're going to go for there. So this is going to get mapped to a space. And then there's other things like apostrophes and stuff. So I want to remove those too. So if we find this, just a single apostrophe, right, like that, we want to map that to nothing. And if we find the reverse, right, so the double quote, we want to map that to nothing. So let's make the reviews cleaned. So the clean version of the reviews is going to be a copy of the original, and for I and range length reviews cleaned, let's go ahead and replace all the strings. For S and string map, what we want to do is reviews cleaned I. So the ith review, we want to go ahead and replace the string with its mapped value, which in many cases is just empty, and then lowercase it all. Right, so all of these were kind of turning into empty. This turns into a space. If you had more characters you wanted to replace, you could go ahead and do it. Sometimes people want to do things like, if you encounter the string can't, you want to map it to cannot and stuff like that. I won't be interested in doing that this time, but that can help clean up the text a bit. So at this point, we have our reviews cleaned, and then we want to transform the reviews into embeddings data frame. Transform. So what we're going to do here is x equals embed. So we're going to leverage the method we defined earlier. So this is going to pass the TensorFlow and embed all these. So you're going to get the 512 dimensional matrix from that. And then we're going to turn it into a data frame so we can work with it a little more easily. And the index of the data frame we're going to set to be the cleaned reviews, basically. So the rows are going to be the actual review cleaned, and the columns of this X are going to be the actual embeddings, and there's going to be 512 columns. And then we're going to return this X, right? So that's what gets returned here. And so we'll have a data set that's kind of containing all that. So let's go ahead and just run that. And let's go ahead and initialize a topic model here so we can kind of start getting a working result. Reviews topic model, and we're going to pass it the side effects reviews, which is the reviews we defined earlier. Right, so we do that. And now if we want to look at what the X is that got cleaned, all we have to do is this. So let's take a look at what that is. But yes, you can see this first index column contains the actual review, and you see across left to right, you've got the embedding columns, right? So this should have 512 columns, which it clearly does. So we go up to 511, starting at 0. That's 512 columns. So that's clearly exactly what we were going for. So perfect. And the next thing we want to do is what we're going to end up doing is the way that the topics are going to be created is that we're going to take the embeddings and we're going to cluster them using KMeans. And it actually is really effective when we use these embeddings. So what we want to do first is find a way to kind of determine how many clusters we should use. That's always a problem with KMeans, like how many clusters should we define for the problem. So let's define a method to determine number of topics, right? How many clusters, right? So this is AKA KMeans cluster number, right? So def, and this, you may be familiar with this, but we're going to create an elbow plot. So the elbow plot, I'll show you what it is, but essentially it's a plot where the x-axis is the number of clusters and the y-axis is the k-means objective, which is kind of the intra-cluster sum of squared distance from the centroid. And basically the way we determine the number of clusters to use with the elbow method is to see where this thing kind of stops decreasing exponentially and starts decreasing linearly. And I'll show you what I mean by that. So let's define a range of cluster sizes. So let's go from 1 to, let's say, 50 or something. No, let's do like, I don't know. Let's go from 1 to 80. And then we're going to do the cluster scores. We're going to accumulate them. So for n in cluster sizes, we're actually going to instantiate a k-means object, and clusters is going to be n. And then we're going to go ahead and fit this thing on self.x, which is the data set of the embeddings. And cluster scores, we're going to append the k-means.inertia. So the inertia is like the k-means fitting objective. And we're going to go ahead and just generate a figure using matplotlib because it's simple. And we're going to look at what this kind of looks like, and I'll explain the elbow method to you. So let's do that. And this time, what we're going to do is topic model elbow plots. So let's see what this looks like. And the elbow plot can take like a little bit to run. So I'm going to go ahead and kind of just skip to the end. So 8 minutes later, we've got this plot. Now this is the elbow plot. So on the x-axis, we have the cluster sizes for k-means, and on the y-axis, we have the value of the k-means objective, which again is the sort of average distance that each point is from its cluster center. And what you can see is that as you have a low cluster count, maybe you clustered k-means with 2 or 3 or 4 or 5, the objective is really high and you're trying to minimize it. And you can see that as you add an additional cluster, it drops super fast, super fast. And then you can see way out here, if you're at 50 clusters, as you add more clusters, the drop is slower. It's like kind of like more linear. It's slower. And the essence of the elbow method is to kind of examine this plot and kind of observe the point at which it starts it changes from decreasing really fast and possibly exponential to something more slow and linear. And by looking at this plot, I think it's super fast here. It starts to slow down, and I want to say maybe from 30 to 40, it transitions from being like really fast exponential to maybe being linear. So the final number of topics we choose will probably be somewhere between 30 and 40. I'm just going to pick 40, but it's really, there's no kind of general, rule that works everywhere forever for this. There is something called the gap statistic, which, again, nothing is guaranteed. At the end of the day, you want to look at different things simultaneously. And what I usually do is look at the elbow plot and then I examine the output of the clustering to see if it makes sense. And then I kind of adjust it from there. But 40 is going to be pretty good for our purposes. It may not be perfect, but that doesn't matter. But anyway, this is how we can determine the optimal sort of number of clusters. And if you really wanted to get fancy, you could fit a exponential linear model to this, and it could be piecewise. And you can determine the switch point by minimizing that function to this data. It'll be a way to automatically detect the number of optimal clusters, but we're not going to do that here. There's no need for that. So we're going to take 40 and kind of run with it. So the next thing that we want to do, now that we've determined that we want 40 clusters, is this goes up here. So we determine the optimal number of clusters. It's going to use 40 clusters, i.e. 40 topics. And so what we're going to do after that is actually create the final sort of model. And what we're missing is we need a method that says, okay, our topic model, we're going to create topics, and number of topics we're going to set to 40. So we need to write this method here. And then after that, we can do something like, topic model. Actually, I won't jump ahead, but basically, let's create this create topics method first. So I'm going to copy this, go up here, and let's do it down here. So method to create topic. Well, extract topics from data. So from tech data, def, sorry about that. So create topics, need to pass itself, and that's what we pass in. All right, so to do this, basically, we just need to first cluster the reviews. So for that, we're going to use the KMeans. KMeans, and number of clusters is what we specify as input to this method, and then we go ahead and fit it to self.x, right? So that's the data frame of embeddings. And then after that, we want to create the final topics data frame. So basically, what is the output of this? We want to create that. So we're going to define that and tie it to the object itself. Topics df is going to be self dot. Actually, just to keep it nice, let's topics df is going to be the output. First, we want to copy the x data frame for now, and we just want to build on it. And what we're going to do is do topics df. We're going to add the topic column, and that's going to just come from the KMeans. So KMeans, once you fit a KMeans, the labels property of the KMeans actually holds the cluster ID for every one of the rows in this topic. So just doing this gives us essentially the topic number, so the cluster ID for which the KMeans put everything into. And then all we want to do from there is just ensure that this is an integer, being interpreted as an integer, because we're going to use it to kind of, slice and dice some matrices and stuff. So we need it to be an integer, not a float. So then at the end, we're going to do self topics df equals topics df, right? And so this is kind of our final result. So let's just run this real quick. Let's reinitialize this. No need to run the output plot again, but let's run this and let it create the topics. And then topic model, let's look at the topics df and see what that looks like. And it has, so we don't need all the embedding columns. So let's go back and remove those. So all we have to do is say topic. We just want the topic column. So let's rerun that, recreate this, and rerun this. We don't need to see a giant, data frame of embedding columns. Okay, so here it created the topics, and now we're accessing the topics data frame, which is the end result. You can see that each of the index of the reviews, the clean reviews, they got assigned to a topic. So let's look at a specific topic and see how that looks. So topic, I don't know, I'm going to pick a random one like 16. So topic 16, okay. Topic 16, if we read through these, it seems to be about constipation. This one mentions constipation. This one mentions constipation, joint pain, arthritis, as well as constipation. So all of this is kind of about constipation. Let's just pick another random one. 20. Topic number 20 seems to be about headaches, maybe? Headache, a dry mouth, and headache. No major side effects, maybe if any, headache. So topic 20 seems to be about headaches. So already the model looks like it's clustering reviews with similar side effects together. I was often tired after a severe headache, right? Headache, dull pain around the side of the head. So clearly this does seem to be working, which is, exactly what we wanted to do. So next, what we want to do is create sort of a summary of this. So each topic, you get an arbitrary number, and it's like the 20 doesn't mean anything. It's just for the k-means to know, which reviews should go with which reviews, and it uses integers to do that. But what we want is actually a summary of the topic. So what is topic 20 about? And for that, we're going to write a little method that is able to come up with kind of like summary keywords. So let's do that next. So to create the summary keywords, what we're going to do is come back up here and we're just going to build on this. So basically want to add create summary keywords per topic. And basically we're going to want to do that like this. So topic keywords, and define that as like a dictionary. So for topic in topics, topic unique. So for each unique topic, what we're going to want to do is extract the topic reviews, which is topics df query topic is equal to format topic. And then we just want the index to list. So the index is the actual reviews that we need for that specific topic. So the query limits the data frame down to the reviews we need, and we access them through that. And then what we need is the topic centroid. So the topic centroid comes from the KMeans cluster centers, and we're going to extract the topic. So topic is the cluster ID, which is what we're using here. So the cluster ID comes from KMeans, and when we do this, we're saying, hey, KMeans, give me, topic number 20's cluster center. That's what this does. And so this is the cluster center. And basically what we want to do, so the idea for coming up with keywords per topic is to say, okay, our cluster center is the average of the review embeddings, or I'll say sentence embeddings, of all the reviews in the cluster, right? So cluster number 15 has, I don't know, 18 reviews in it. And the center of that topic cluster is the average of the vectors of the samples that are in it. And those are the average of the word embeddings. And so the idea here is to say, if we can iterate through all of the words in the reviews for that topic, the words in the reviews, we can embed the words using the sentence encoder, the universal sentence encoder, and then we can see how close that word is to the topic centroid at the cluster center. And that's kind of the rationale for doing this. And it actually turns out to work pretty well in this case. So what we need to do here is topic keywords. What we're going to do is say, okay, so for that topic, we want to do self.get closest words. And that's going to be from topic reviews, and we're going to pass in the topic centroid. So we need to write this method. But basically what this is going to do is going to get the closest words that exist in here to this centroid. So out here, we're going to write a method, def closest words, self. We need the reviews and centroid. Okay. So what we need to do here is pretty simple. Let's maintain a word distances dictionary. So for each review in the input, I want to get the review words, right? So the words in the review. So W for W in word tokenize R if W not in self.stop words. So what am I doing here? I'm saying give me all the words. So tokenize the review and give me all the words, but only give me the word if the word is not in the set of stop words. And that's where we're going to use some NLTK. So right up here, we're going to specify an attribute stop words, which is going to be NLTK. No, sorry, it's going to be stop words English. So basically, we're asking NLTK to give us, the stop words basically. We're also going to need something else here called the embedding dimension, which is 512, and that comes from the USC encoder. That's going to be handy. So this is a stop words from NLTK. And by the way, stop words are just nuisance words. They're like words like of, the, is, that, right? Things that would never be keywords, we don't want to consider those, right? It's just a waste to consider them. So we're gonna accumulate all the words that are not stop words, and then what we do is for word in review words, what we're gonna do is get the word embedding. So we're gonna use the embed function again on that word, right? This returns a 512 dimensional vector for the word W. Then what we're going to do is calculate the distance between, so how similar is the word embedding to the topic's centroid, right, which is the average of the cluster samples embeddings, right? So that's kind of the key assumption here of how we do this. So word distances. So we want to update this, right? So for the word in question, we actually want to get the cosine similarity of the word embedding with the topic centroid. That's what we want. So how close is this to the centroid? And so we need to write this method. But basically what's happening here is we're calculating those distances for each word, and then when we're done collecting distances of the words to the topic's center, what we want to do is take the top 5 keywords. And that's the way we're going to do that, is say, okay, so give me the word. So give me for W in word distance. So for all the words that I looked at, give me a list where the first element of the tuple is the distance and the second element is the word. And then what I want to do simply is just sort this. And sort this ascending. So the first elements of this list will have the smaller distances, and it's just word such the cosine similarities, right? So this is going to sort from low to high in terms of cosine similarity, and so the ones we want are going to be the last ones in the list. So maybe the last 5, because the cosine similarity, if it's 1, it means match. Closer to 0 means different. So this is going to sort this list from 0 to 1. So we want to take the right end of this, which is the words closer to 1, so more similar. Then we're going to return just a comma separated of the words. So for X in top 5. So basically, for this list of 5 keywords that are most close to the topic centroid, give me the first element, not the 0th, but the first element, which is just the word, and string them all together with a comma separated. And so all we need to do here is calculate this cosine similarity, which is pretty simple. Def cosine, let's just copy paste this here because it's so much easier. Cosine similarity, give itself, and just make it arbitrary vectors here. Cosine similarity between 2 vectors x and y. First thing we want to just make sure is that x and y are both the appropriate dimension. So x reshape it to be that embedding dim, and then y is the same, reshape self that embedding dim. So that's why I defined that earlier, just so it's globally accessible. Up here, the embedding dimension is 512. So there you have that. And then we just calculate cosine similarity. So the formula for that is first you calculate the dot product between x and y, which is pretty simple. And then you need the x magnitude, which is x dot x square rooted, and the y magnitude is y dot y square rooted, and then you just simply return the dot product divided by the x mag times y mag, and this is just kind of your standard, cosine similarity measure, and then so this returns returns closer to 1 if x and y are similar, closer to 0 if they are different. That's what this does here. So now the get closest word is going to return a string of the keywords. So it gets saved here, right? And then what we want to do at the end is build this into the topic data frame that we're going to return. So we're going to write topic keywords. So the final keyword set is going to be, and this is topics with a plural. It's going to be topics df topic. But we're going to map what we're going to map. So these are integers, right? And so what we've accumulated here is the integer to string mapping for the keywords. So all we have to do is pass that in, and the map method knows how to basically map the integer topics to the string keywords that are comma delimited, and that's what you get there. And now we just have to add this topic keywords to our output data frame, and we also want to make the keywords by topic accessible from outside. So we do that by just pinning it to the self attribute. While we're at it, let's go ahead and score the sentiment of each review, right? So that's actually pretty simple using the handle function from up here, way up here, where we can leverage the sentiment model. So we're going to use this. So let's come back down. It's actually pretty simple, very simple. All we're going to do is say topics df sentiment going to equal the list sentiment. We call the method R for review, for R for R in topics df index values to list. So basically, for the index of the topics data frame contains the actual review. So for every review in there, pass it into the sentiment method and let that return the list of sentiment scores. And so let's go ahead and add that here too. So sentiment. And so that'll all return the final data frame that we're interested in. So let's go ahead and run that. Reinitialize the model. Don't need to rerun the elbow plot. But let's go ahead and recreate the topics and examine the output once again. And this will probably take a little minute because it's got to search through all the keywords and do all that stuff. So let me just go ahead and skip this and come back when it's ready. So finished running, we actually ran into an error. And the error is something I caught before, but I forgot to address it. But basically, it's saying token indices sequence length longer than the specified maximum sequence length for this model. And what it's referring to is the sentiment part of the model here. So basically what it's saying is the sentiment model that's working from the Hugging Face platform can only deal with strings that are 512 length character long. So it encountered one that was longer than that. And actually, Hugging Face models tend to have that. So some models have maximum sort of sequence lengths. So it's pretty easy to address here. So if we come back up in the sentiment scoring method, all we have to do is cap this at 512. That's really it, and then it'll work. As long if the review is super large, okay, we don't really care. There might be better ways to do this, but for now, we're just going to limit the input string to be a 512 and see what happens. So I'm going to rerun this and then rerun the topic. Don't need to run the elbow method, and now let's recreate these topics. Probably take about 8 minutes, so let me come back when it's done. Okay, so that finished running and it ran successfully. So now let's look at some topics and let's actually layer in some of the keyword stuff. So let's see. So let me do topic 20 again. Let's see what this returns. So topic 20 says the topic keywords, which are repeated for each topic because it's all the same per topic. Nauseous, nausea, all the nauseous type stuff. So if we read through these individual reviews, it says nausea for the first 2 weeks. Patient felt mild headaches in addition to their mild symptoms of nausea. Unfortunately, there were many symptoms. Nausea is included. nausea. I've taken on an empty stomach. Only side effect was nausea. On a few occasions, nausea immediately, nausea, vomiting, depression, so on and so forth. So topic 20 seems to be about nausea. Let's look at a different topic. Topic number 24. It's funny. This one has to do about, I guess, erectile dysfunction and libido and stuff like that. So that's what the topic keywords seem to be about. So you got, horniness, moodiness, impotence, erectile, libido. So things related to sexual function. So this first guy saying he got low sex drive from it, which is interesting. This person's saying he has no sexual desire. Sexuality is not good anymore. So decreased sex drive, could no longer have orgasms, not interested in sex. So clearly, topic 24, the keywords are reflecting accurately what it's about. Let's just pick another random topic here. Topic number 35. So the keywords here about cravings, pounds, swelling, gaining weight. So probably about gaining weight. So let's see. This first review says gain weight a bit. Next one is weight gain, severe appetite loss, and some weight loss. So actually, it's not just about weight gain. It's just about weight in general. But many of these say weight gain, weight gain, loss of appetite, right? So even though this isn't about weight gain, right, the fact that it's about loss of appetite is associated with the topic here, the topic keyword still, even though loss of appetite's not showing up here. So that just shows you that the semantic stuff is working pretty well. The rest of the stuff here you can see is about weight gain, swelling, weight gain, fatigue, weight gain, weight gain. So you can see there's erectile dysfunction here and weight gain. So we just saw that the previous topic was about libido and erectile dysfunction issues. So there's still some overlap among the topics. So we may increase the topics from 40 to 50 or something higher. And this is where you have to kind of just use your sense. Like you have to review the output and determine what the optimal number of clusters is. That being said, the topics are definitely, the reviews are definitely clustering in as like for like. So the clusters are definitely a good quality, even though there's some overlap. So I think that's pretty interesting. And like I said before, just to show you, topic model has tied to it topics keywords. So if you go to topic number 35, you can just return what the keywords are. So it's a way for you to know, by topic, what is it about? Kind of a quick glance, what is the topic about, right? And the last thing we want to look at is some of the sentiment. Some of the sentiments that return here are positive. So like most of the sentiments are negative, and that's because we're talking about side effects. I would expect the bulk of the sentiments here to be negative. I mean, we can actually systematically look at that. So let's do this. We're scoring sentiment on um, a per review level, which means that we can calculate the average sentiment per topic. But see, now for this topic, which is about like impotence and sexual dysfunction, I see there's actually a positive sentiment one here, and this one says no negative side effects, improved skin, more libido were actually benefits. So actually, that's interesting. So this topic 24 is about I guess, sexual function, and most of it's negative, but a small amount of it might be positive. So that's really interesting. So this method that we're developing not only develops or extracts topics from the text, but also tells you the polarity. And so a certain topic may have more or less positivity, and that's something interesting you can look at. So here, let's group this by let's do summary topic keywords, which is what it's called, correct? Topic keywords, and let's go ag. So we're gonna sentiment, want to average this, right? And then let's do reset index, and why don't we go ahead and sort values by sentiment, and let's see what this looks like. So we see at the top the most negative sentiment, is for things like headaches, sickness, vomiting, nausea, right? So topics having to do with nausea, tendonitis, and pain, body pain, fibromyalgia, pains, body pain. So these are highly negative stuff. Itchiness, rashiness, highly negative. But let's scroll down all the way to the other end of the spectrum. So here down here, we could see um, this one, for example, says never, negative, haven't, anything, none. So that's interesting. It's got, all of it's still negative, which makes sense because all of it is about, side effects. But it's interesting. The ones down here, I'm curious for this topic 28. Let's look at this topic 28. Topic, topic model query. Topic equals 28. Let's look at this one. Whoops. Topics df. So, I picked the wrong one. Oh, sorry, that's not the topic. That's not the topic. I need to include the actual ID in here, which is just the topic itself. Let's rerun that. So that one was where it was like a negative. Let's just do this one. This one has the lowest sort of sentiment score, right? So the least negative. So if you plug in topic number 19 here, what is this one about? So this one's actually, a lot of them are saying no side effects, which explains why the sentiment is, not all the way close to -1. It's actually smaller than that. And it looks like in some cases there were no side effects is judged as a positive thing, and then here there's absolutely no side effects just as a slightly negative thing. I think what's happening is the sentiment model's not great at picking up the difference between these two things. It's kind of like all good or all bad. But here you can clearly see that when you calculate the average sentiment per topic, that this topic happens to have, the least negative. And when you look at the actual reviews, they are indeed the least negative. They are indicating no side effects. So actually, the sentiment model is at least directionally correct. So there you have it. There's the complete model. So I think it's working pretty well. I think this could work great on any other data set of reviews where you want to extract topics from them. So that's pretty much it. I'll be posting it to the GitHub. Hopefully it's useful to you guys, and please like, subscribe, and all that stuff so you can, keep up to date with the content I'm putting out, and hopefully it's useful.